I think you are able to view my PPT.
Yes, sir.
Okay. Okay. Today we are going to start. The chapter is clustering. I think what we have done till today is that we have done this association mining, and then we have done this classification. Now we are moving to the clustering part. Okay. As you know that this clustering is a unsupervised learning. So let me know. Let me check this. Okay. So we are going to uh, discuss the clustering part. As you know that it's a unsupervised learning. Okay, fine. What does it mean is very simple, that you have data D in which the class label is not known. Okay, fine. So whatever features you have in the data D, use those features and then cluster them. So by virtue of the feature characteristics and properties, the methods are applied and we are getting set of clusters. Okay, fine. So these set of clusters I can have, like suppose if I go for say two-dimensional hyperplane, then suppose there are points like this, then I can say that this is my one cluster, this is my second cluster, this is my third cluster, and these are outliers. These can be referred as outlier, whereas these are C1, C2, and C3. So, and what parameters you have used, what metrics you have used? We have used the distance. Certainly, if I'm looking for distance between 2 points, so I may be Euclidean distance I'm looking for. Okay. So, you can see that what does it mean is clustering of data is a method which a large set of data is grouped into clusters of small sets of similar data. So this is what clustering does. So what you look for is that you look for high similarity to the intra-cluster data, whereas what you look for is that you always look for dissimilarity of interclusters. Okay, right? So what you are trying to maximize the intercluster distance, whereas we try to minimize the intra-cluster points distance. Okay, so this is what we actually look for in the clustering part. So since class level is not known, so it is referred as unsupervised learning. Okay, fine. As far as application, I think it is widely used in pattern recognition. It is again used in spatial data analysis, where actually you are looking for spatial clusters. Uh, Very much widely used in image processing. Then some market driven research also required such methods. Then we have document classifications, then some clustering of log data uh, to discover the similar access pattern within the server also could be the part of the work. You can have some examples of clustering applications like marketing. You can see that certainly I can discover distinct groups in their customer bases. We can actually have some, we can actually detect some knowledge to develop the targeted marketing programs also. It can be used for earth observations. It can be used in insurance also, like identifying groups of motor insurance policyholders with a high average claim cost. So this might be one query from any insurance company. So you are looking for that. Then similarly, city planning, then earthquake studies, all these could be uh, prominent applications. How this clustering actually evolved. This is one example, which is a famous example. Certainly, this example is from the country England, where actually way back there was a cholera outbreak in London. So a physician plotted the location of cases on the map. So what it does is, so it actually started looking on the cases coming from all the parts of London, and he actually considered the map of the London and that's trying to figure out the from where the most of the cases are coming. Okay, so what he actually found is that like suppose this is some group of patients, then another group of patients, then another group of patients, and there is few patients which are coming from other area. So uh, actually what actually was considered during that period is that since this is the area where actually the outbreak is going on, so the actually the management or the government can take decisions that what to do, what to take the measures to prevent this cholera outbreak. So they have focused in the specific area where actually the disease cholera was actually having the most of the cases. So it actually actually provided the ease in the management, because you can always issue the instructions to these areas that okay fine, uh, just clean your surroundings, or put some sort of say water cleaning chemicals in the water, uh, clean the drain. So and obviously more doctors can be uh, sent to this particular part. So such measures you could take just plotting the patients on the map. So this was the I think early observations, and that actually evolved this clustering application. Okay. So that was the case. Uh, these are again some examples. So this you can see that like the first these are some examples. These are three examples where actually what you are looking for is you are looking for group of homes. Then there is geographical distance based, and then size based. Okay, so this is the same set of data, and what we are doing is we are considering in a three different metric to get the clusters. In first case, what we are looking for is that dense group of homes we are looking for. So obviously, these are the group of homes. You can see that this area is having more homes, whereas uh, whereas this part is no home, this part is no homes, this part is no homes. So the moment I talk about that I'm looking for geographical distance, that means distance between two houses, or this like this. So by putting some sort of threshold that okay fine, I'll be saying that okay fine, if it is 50 meters, then I'll be considering it is within the one clusters. So what we found is that we made one cluster, second cluster, third cluster, fourth clusters, and there is one outlier also, which is also referred as, sometimes we referred as clusters. So this is what set of clusters you could get when you are looking for, when we are actually considering the distance based clustering. The moment you change your clustering basis, what we do is that we are looking for uh, home size based cluster. That means you know that homes are actually having a different size. So I may be interested to have one story homes, two stories, three stories, four stories, say 10 stories of home. Then you can see that what is happening out here. That this particular set of clusters might not be the case in this case also. So you can see that there are few homes which is coming from this cluster, and few homes are coming from this clusters, and this actually makes one cluster of one size home. Similarly, some size like one size is this, another is this, and this, and this. So based on what features you are considering and what metrics you are using for cluster formations, depending upon that, the cluster formations get changes. Okay, so this is one example. So always remember that uh, you are applying clustering on the same set of data, but if you use different metric for in iterations, then you will be getting different set of clusters out of it. Okay, so this is what we do it. Now let us define the clustering problem. It says that given a database D, where actually you are looking for set of uh, tuples, say records, then we are looking for an integer value k. The clustering problem is to define a mapping which is f d to g. G actually varies from 1 to k, where each ti is assigned to one cluster k. Okay, where j is actually taking value from 1 to k. Okay, fine. This is what. So a cluster kj. So I can have k1, k2, or kj like this. So some of the tuples will be mapped to this, some of the tuples will be mapped to this, some of the tuples will be mapped to this. So this actually forms individual clusters. So this is what the problem of clustering. Okay. Obviously, this is not same as classification problem, where actually we are experiencing the supervised learning, where cluster classes are known to you, whereas in clusters, classes evolves during the clustering process itself. Okay. In some cases, in some sort of methods, you can actually fix some of the classes. Say, like in case of k means, we can fix what would be the k. So if I fix k equals to 5, then certainly accordingly the 5 clusters will be formed. Whereas if I fix k equals to 3, then 3 clusters will be formed. So depending upon the user defined parameter k, the corresponding number of clusters will be found. But always remember that I can fix the numbers, but I cannot fix that what sort of features would be for these clusters. This will be evolved during the clustering process itself. Okay. So difference as far as clustering and classification is there. In case of clustering, there is no prior knowledge. That means number of clusters or meaning of clusters. And clustering is always referred as unsupervised learning. There are some issues in clustering process, like always this is an issue that how to handle this outlier handler. The problem with this is that suppose I say that these are the clusters. Say like this. Say that I say that okay, these are the prominent clusters I have. Now these are the outliers. So obviously these outliers should be ignored because individual points clusters may not be having the significant use. But always this is questionable that why not these three comes in one cluster. Can we have a cluster of these 3 points? Or there may be a case that at present it may not be, it is a sort of noise, but in future if data is coming continuously, then there is a possibility that there is a dense point as around that point may occur. So in that case, this need to be declared as clusters rather than still be the noise. So such issues need to be handled. Dynamic data is always is very interesting in nature. Reason just like I told you that this outlier discussion always depends on whether you are working on dynamic data or a static data. So dynamic means always data is updating, and static means that at particular instance you consider the data D and then you work on that. Then the issue pertaining this evaluating results is again is very interesting, because what you have is that you actually finally you get the clusters, but how to interpret these clusters? Like that means normally in classification what we have is that you know that this is cluster, these are data, and this how this mapping is going on. So we get rule out of it. So but in this case there is no such rules actually evolved. So how to evaluate the clusters, how to evaluate the results. So how to get this what you call it as characteristics or properties of the clusters. So this part is very interesting and important and critical as well. Then number of clusters, as you know that in some methods number of clusters can be defined by users, but most of the methods you actually depend upon the clustering method itself, that how many clusters it can generate. So depending upon number of clusters, suppose your requirement is that I would get 3 clusters but you are getting 5 clusters, so that becomes issue for you. You are looking for 5 clusters but you are getting 3 clusters, again there will be issue. Why I am saying this can be a part of issue? The reason is, suppose you are looking for, say there is a company who looks for that you have 3 executives, 1, 2, 3, and what you want to have is that you want to have a set of visits for all 3 executives, pertaining that you look for minimum cost or minimum distance to be covered by the respective executives. So suppose you have only three executive, but you get five clusters. Then you need to have some sort of cluster merging criteria where actually out of five you can generate three, or out of five you can generate out of three you can generate five also. So both the things can be a part of your. And then scalability is a very important issue. Reason is that normally what we get is, just let me erase this. Okay, suppose you have a s size of data. So d is of s. You apply some method m1, you get a very good result. The moment this s becomes s1, so what we get is that this method 1 is not efficient. That means it is not giving a good result. Also, it involves high complexity. That is the case. So the question always be there that if a particular method is good enough for a small size of data, how to scale up so that the large amount of data can be used for the clustering purposes. And obviously, in today's world, we are actually having a large base of data, and we always look that in one go, can I go for mining techniques to be applied so that I can get some sort of knowledge out of it. So these are the issues which clustering is actually carrying with it. The next what we are going to discuss is that certainly you have data D, and obviously this is T1, T2, T3 or Tn. So tuples are there. But normally what happens is that directly I cannot use this data for my clustering purpose. So there are a set of algorithms which requires these data need to be transformed mathematically. Okay. So for that purpose, we actually look for data matrix. We also look for dissimilarity matrix. We also look for some data types which can be used for a very which can be used for clustering purpose, and which actually gives you ease in the process also. So for that case, we'll be going for this part. I think most of the things you are well aware of. Like suppose what is data matrix? You know that data matrix is nothing but its object by variable structure. So represents n objects with p variables. That is, when I say variables means attributes or measures. So this is nothing but this is n by p matrix where n objects and p variables are there. Okay. Now the question is how to get this, how to actually transform this particular matrix into dissimilarity matrix. So you can have this. So the moment I look for dissimilarity matrix, so I'm looking for object by object structure matrix. Like suppose what you can do is that I can tell you that okay fine, these are cities, say C1, C2, C3, Cn. So in previous case, what we have is that these are the distances you have, okay, which particular like these are the variables you have, which actually talks about, like suppose what we have is Let's suppose what you have is, say, I'm looking for, just a minute. Say I have an object like x1 and x2, and certainly what we have is some values corresponding to say a1, a2, and ak. Similarly, a1, a2, and ak. So these are two. So these are two objects we have. Now what I'm looking for is, what is the difference between these two, okay, x1, x2. Say if I look for this, okay. So dij is the measured distance or dissimilarity between objects I and j. It has always been non-negative and near zero when objects are highly similar. For example, what we have seen is this is, so if I say that Cn, C2. So what this zero corresponds means, this is a distance between CT1 and CT1. So obviously, if I am looking for distance between Allahabad to Allahabad, it will be zero. So all diagonal will be zero, because this actually talks about distance from city to that city itself. Whereas others like this talks about the distance between city to city1. Suppose this is C1 is Allahabad and this is Lucknow. So these values will be nothing, but suppose this comes as 200 kilometer. So this 200 is actually your D21. Okay. So similarly, all corresponding distances between the cities can be fitted in this matrix. So this becomes your object by object structure. The best part is that either lower triangular matrix or upper triangular matrix will be sufficient for the clustering purpose, because actually upper triangular and lower triangular matrix are same. Okay. Any query till now? Till what we have discussed? Any query? So we'll move forward. So obviously, the reason of deriving this dissimilarity matrix is that many clustering algorithms operate on dissimilarity matrix. So if data matrix is given, it needs to be transformed into a dissimilarity matrix first. Certainly, the question always be there: how can we assess dissimilarity Dij? This is not easy to get it. Certainly, like there are some distance formula through which I can do that. But we have to see some data types which could be very much useful for deriving this dissimilarity matrix for clustering purpose. Okay. So data types are the interval scaled variables, then binary variables, then we have nominal, ordinal, and ratio variables, and then lastly we have variables of mixed type as well. Okay. The first one is interval scale variables. This is continuous measurement of roughly linear scale. Like suppose what you have is like weight, height, latitude, longitude, coordinates, temperature you have. So these are these could be like, you know, that these could be my attributes or features for the clustering. So how to deal with this such attributes? Okay. Certainly, as far as effect of measurement units is concerned, when you are using a smaller unit, certainly there will be a larger variable range. When you are going for a larger unit, there will be a smaller variable range. So obviously the effect will be larger in that case for clustering structure. So we need to do some sort of standardization also. Then you require some background knowledge to do that. For example, suppose you look for clustering the basketball player, then certainly you will be interested to give weightage to the height, because you know that height is a very important feature for any basketball player. Okay, so that is we look for. Can anybody can tell me that why this statement is written? Uh, that a smaller unit than larger valuable range. Can anybody can anybody tell me what does it mean? See, one thing. Suppose take the example of height itself. So height could be like, suppose sometimes we say that, okay, what is your height in centimeter? What is your height in feet? What is your height in inch? So when I say that, I can say like 170 centimeters my height. Then when I go for feet, then I'll be saying 5 feet and some sort of 8 inches there. Only inch I'm looking for. So something like say uh, say 65 inch. So what is happening in this case is you can see that when I say when I consider this centimeter, then I'm getting a large sort of volume is 170, whereas if I go for feet, then I'm getting just 5 to 6 feet, whereas if I go for inch, then I get some sort of 65 inch. So what is happening is, like suppose if I say if I'm looking for there are two objects x1 and x2. When I say objects in this case, that means some player 1 and some player 2 I'm looking for. So if I go for the distance between these two, so in terms of fit, the distance will be very less. When I go for in terms of inch, distance will be a bit larger than this. When I go for in centimeter, the distance will be like this. So that is what it means. Okay, so this is the case. Okay, so it depends upon your requirement that what unit you are looking for. That means suppose I'm just looking for centimeter to be there, then certainly you have to transform the entire attribute values if it is given in feet or inch into centimeter, or vice versa as well. So that is what we look for. Okay. As far as standardization is concerned, then certainly obviously you have the data matrix, so you can always go for mean absolute deviation, which is nothing but this, and then you you can calculate the mean, which is this, and then z score I think can be calculated using this. Okay, fine. So some sort of standardization can be achieved through this. uh, Obviously there you can always question that why we are using mean and absolute deviations rather in place of standard deviations. The reason is very simple, that using mean absolute deviation is more robust, as in that case z scores of the outliers do not become too small, so they remain detectable in that case. Okay. Distance, certainly I can make use of Minkowski distance, which is this, And by putting q equals to 1, I'll be getting some density distance. Then if I'll put q equals to 2, then I'll be getting Euclidean distance. And then if I put some weight, say W0 or W1, W2 or W3 or Wj, then it becomes a weighted distance. Now I can tell you one thing is that why this weighted distance is very important. Reason is, suppose I'm looking for a Euclidean distance between two objects. Just now we have seen that x1, x2. Okay, so you know that these are the features or attributes respectively. Say this is weight, this is height, this is, say, something qualification or something, like there may be any number of features you can select. Now, since I know that for a particular basketball player, this height is very important. So I can assign weight higher than others. That means I can assign high weight to this so that the impact of height always be higher when I go for dissimilarity between this x1 player and x2 player. So in that case, this weighted distance will be very much useful. Okay, fine. So I'll move forward. These are normal properties that Dij should always be non-negative. Uh, Dii will always be 0, and it should be symmetric, and triangular inequality will be preserved. Okay. Next is binary variable. This is very interesting one. Binary variable, always I can, like, you know that binary variable can be represented in terms of 0 and 1, or say no or yes, or absent and present. So any sort of ways you can actually create a binary variable. So this is object J and this is object I. So I can say that this is, some say a player 1 or player 2, something like that, and then I'll be looking for this. So if it is both is 1 1, then I'll be assigning A, then 0 1 C. So A is 1 1, B is 1 0, C is 0 1, and then D is 0 0. So this is what we have. Okay, fine, corresponding to each of these variables. Now, simple matching coefficient invariant if the binary variable is symmetric in nature. Then the distance can be calculated in terms of this. Whereas if it is non-invariant and variable is asymmetric, then I'll be having this formula, b plus c by a plus b plus c. Always remember, when I say symmetric and asymmetric, that means, suppose if I say that sex, I can have male and female. Okay, suppose I'm having this. Then if I say that if not of male corresponds to female and not of female corresponds to male, then it is symmetric in nature. If this does not hold, then it is asymmetric in nature. So attribute could be asymmetric or symmetric in nature when I look for binary variables. Depending upon that, these two formula can be used. Fine. So this is one example taken from the book itself. These are three patients, Jack, Mary, and Jean. Now there is attribute like A1, A2, A3, A4, A5, A6, and A7. Okay, fine. These are the respective values. So what we are assuming that YP is 1, because this actually present an yes, and N is set to be 0. So you can see that 1 1 1, 0 0 1, 1 1 0, 0 0 0, 0 1 0, 0 0 0. So I can assign these values to this. Assuming that gender is the only symmetric attribute, rest are asymmetric in nature. So now I'm looking for the distance between this Jack and Mary. So obviously the formula, I think you must remember that B plus C plus A plus B plus C. Now what you have is A is 1 1, B is I think 1 0, C is 0 1, and D is 0 0. Okay. So just count the instances. B is 1 0. So Jack and Mary. So just check that is there any 1 0? No. So it is 0. Now C is 0 1. So there is one instance. So it is 1. Now D is 0 0. So there are instance like 1, 2, and 3. Okay. So there are 3 instances of 0 0. Just a minute. A plus B plus C, B 1 0 0 0. Okay, fine. Fine. Yes. So you can see that there are 1 1 instances. There are 1 1 instances here. So 2 is coming, and B is 0, C is 1. So D is not required to be like the there is no D instances in this. So this is my required data, and it actually generates 0.33. So this actually says that Jack and Mary is actually dissimilar with the ratio of 0.33. Similarly, I can go for Jack and Jim, which will come as 0.67, Jim and Mary, which will come as 0.75. So obviously this has high dissimilarity, this has again higher than the first one, and this has lowest dissimilarity between the patients. Okay. So depending likewise you can actually find out. So once you get these dissimilarities, this actually can be like this actually can fill the data what we have is object by object matrix. So I can say Jack, Mary, and Jim, then Jack, Mary, and Jim. And then certainly I can say Jack, Mary is this. This will be 0.33. Then Jack, Jim is 0.67. Then Jim, Mary is 0.75. So likewise you can generate your matrix, and then you can use it for the clustering. Fine. This is what the binary variable, and this is the way you can actually tackle the binary variables, and you can have dissimilarity between the objects. Always remember, not necessarily that all the attributes should be binary in nature for particular data set, or all the entire data set should be in the same data types. It can be of mixed also. So the dissimilarity can be generated in different manner. Now the next is nominal variables. Generalization of the binary variable in that it can take more than 2 states. Like suppose I'm looking for colors. So say you have 4 colors. Okay, fine. So there are 2 methods you can do that. What we have is that actually this is not restricted to the 2 states, rather than it can take multiple states. Like in this case, color is taking 4 different colors. So the method 1 is that you can generate this Dij by P minus M by P, where Pm is number of matches and P is total number of variables. So you have 4 variables, then number of matches you can have from data. So it can generate Dij for you. Whereas in this case, what we have is that I can create a new binary variables for each of the m nominal states. Say for red, I can generate uh, yes red or no red. So this becomes two binary variables. Similarly, I can go for yellow, yes yellow, and no yellow, and then treat them as binary variables and make use of the formula for calculating the DIJ. So this is how these nominal variables can be used for the clustering purpose. Always remember that when you are tackling some sort of attributes which actually can take some limited number of states, and you can say greater than two states, can be tackled with this nominal variables cases. Okay. Now the other one is ordinal variables. Ordinal is very much uh, prominent in data. Like suppose you know that there are some attributes where actually the ranks are very important. Like suppose if I say faculty, you know that there is assistant professor, there is associate professor, then there is professor. Sometimes we say lecturer also. So there is a hierarchy in this attribute. Okay? So there is a rank involved in this attribute. You know that lecturer is the lowest one, then assistant professor comes, then associate, then professors comes, and later on you can say senior professors as well. So there is a ranking mechanism in this. So what you do is that you are looking for standardization with the consideration of the ranks. So in such for such attributes, what we do is that we actually replace the XIF, which actually we have tackled in the interval scaled, with RIF, which is nothing but the rank. Okay, and then Z score formula is revised with the consideration of the ranks. So it will give you the rank minus 1, then MF minus 1, which is actually the standardization of the data. And then using the distance formula, likewise we have done in interval scaled, you can generate DIJ. So this is how we can actually tackle the ordinal variables. Okay, fine. Then there is another case is ratio scale variables, where actually this is somewhat like sometimes it is useful because data may be having some sort of non-linear scale or approximately exponential scale. Say where actually you are looking for some e to power something. So what the methods as far as is concerned, that you cannot consider them as interval scale variables because that might not be the good choice. So, what you can do is, the best part is that you can apply some logarithmic transformations and you can actually have this and then treat them as continuous ordinal data. Okay, and then same like use rank, and then again the same way what we have done in interval scaled can be used for that. So the only thing is you cannot directly considered or cannot directly transformed into interval scaled, rather than go for the ordinal data and then go for the interval scale. Okay, fine. There is there may be a case, as I told you, that it is not always the case that data will be having one type of data, rather than it can be of mixed type of data. So I can have symmetric binary, asymmetric binary, nominal, ordinal, interval, ratio. There may be. So what you can do is that the DIJ can be formulated with the mixed variables, where actually I can say that, okay, fine, some data is binary or nominal, some data is interval scale, then some data is ordinal and ratio scale. So obviously in that case, what you need to do is that if it is ordinal and or ratio scale, then obviously you know that you have to go for ranks to be incorporated, then if it is interval scale, then mean absolute deviations will be considered. If it is binary and ordinal, then certainly we have seen that whether it is asymmetric or symmetric, that could be used. So you can merge all these distances, and you can compute the uh, mixed type of dissimilarity of two objects ij, and can be used for clustering. So that is what we are doing. Okay, you can check that. There, I think there is some sort of check with the book this formula again and go with the correct one, because I think there is some sort of mistake in this formula. So check it. Okay. Now, since what we have seen just now is that what are the different types of variables we can consider it, and how these variables can be used for generating the dissimilarity between the objects. And once we are able to have this dissimilarity between objects, then we are able to generate the data matrix. Okay. Now, once you have actually that you have applied the methods and all, and you get the clusters. Now the question is how to get the distance between these clusters, like this. So like suppose if this p minus p dash is the distance between 2 points of two objects. So this is 2 points. Now mi is mean of the cluster ci, and ni is the number of objects in ci. Then the distance between clusters can be computed, say ci cj can be referred as this. Okay. What does it mean is very simple. Suppose there are two clusters. So it says that from all the points of these clusters and all the points of these clusters, just compute the distance between these two. So all permutation and combinations will be there. So all combinations will be evaluated, and then the minimum will be. Okay. So minimum distance means I can say that, okay, fine, this is the point, this is the point, this distance might be the minimum if you look on these two clusters. So this distance is talking about this distance. Obviously, when you look for large amount of data, this cannot be visible with this plot. So this formula can be useful in that case. Similarly, this can be referred as the distance between these two clusters. Now, the other way is that instead of going for this, I may be interested to have this. So the distance between these two. So the maximum. So what is the maximum distance between these two can be figured out. That individual data points distance with the individual data point distance of the other clusters can be calculated, and the maximum will be. Okay. So this is, and this can be also considered as distance between clusters. This is maximum distance between the clusters, and this is minimum distance between clusters. Similarly, there will be a mean of this cluster, there will be a mean of this cluster. So this can give you the mean distance between these two clusters. And the fourth one is average distance, which is nothing but what we have is that you get all the distance between the points of the two respective clusters, and then all these will be added and then divided by the total number of points of this and total number of points of this. So this will give you the average distance between these two clusters. So this is depending upon your requirement, you can actually use this. Okay. Okay, fine. Uh, I'm just giving you a 5 minutes break, then I'll come back. Okay. Resuming the class. I'm audible to all?
Yes, sir.
Okay. Slides are visible?
Yes, sir. It's visible.
Okay. Okay. So as looking for this, like we have seen that how this distance between clusters can be computed. Depending upon requirement, any distance can be considered. Okay. Uh, Distances, I think we have already seen. So what is good clustering when we look for? Then a good clustering method will produce high quality clusters with high intra-class similarity and low inter-class similarity. This is something is we are looking for. That we always look that uh, the intra-class points should be very close in terms of property. So it should be similar also, or in terms of distance, you can say it is close. Whereas we look for low interclass similarity, that means the interclass points, data points should be far or dissimilar in nature. As the clustering uh, quality always depends on how far or how dissimilar the interclass and how similar the interclass is. Okay. I think this we have already discussed that how this outlier is creating problem. These problems actually can be detected by some statistical technique. There are some methods, there are some clustering algorithms which actually, by default, it actually take care of outliers and it also eliminates outliers as well. And there are some algorithms which actually do some outlier analysis also. Uh, as far as real time or real life data, then this outlier uh, analysis, normally we ignore it, but in some cases it becomes relevant to explore this outlier also. So there are some tests available through which we can do that. As far as clustering approach is concerned, then there are four different types of categories are available. Like there are some algorithms, some methods which is hierarchical in nature, then partition, density based, grid based, and all. Like in hierarchical, you can see that some sort of uh, uh, single link, then agglomerative and divisive algorithms are there. Then Birch is there. There are so many algorithms which actually comes under this hierarchical. Whereas in partitioning, we have k-means, then k medioids, that is partition around medioids, and then we have Clara, we have Clarence. So there are similar density based like algorithm like Cure. Then we have DV scan. Grid based, there are like Cobweb, and there are algorithms uh, which sometimes referred as density based, sometimes it is referred as grid based, and all like optics is there, and then and there are many more. Okay. Obviously, there are some algorithms which deals with the uh, dimensionality also. You know that this actually leads to what you have is that then in terms of dimensions, you look for low or high dimensions. Then there is what we call it as curse of dimensionality comes in picture. Then obviously you move to some ML and deep learning. There are so many which actually you can do in this. Okay. So the thing is that when you go for ML and DL, this actually also considered the classification part. So some clustering and classification mixed becomes your machine learning and deep learning. Okay. So what we do is that I think category is very much evident in this case. So what we do is that uh, in the next class we'll be doing this partition based hierarchical, density based, and then grid based. So we'll be doing one by one the algorithms available in this. Just to start with clustering, uh, I'll be uh, just a minute. I'm giving you just an idea that how this K means works. K means is actually is a partition based algorithm, partition based clustering. It is very simple. Like suppose say 4, 12, 35, 26, 9, something like this. If you have suppose these are the numbers and you look for clustering. Okay. So the first thing which you can do is that fix K. So you can fix K as 2 or K as 3, anything you can fix. So I'm fixing as K equals to 2. Now what you can do is the moment K equals to 2, that means I'm looking for two clusters. Now then M1 and M2, there will be two mean for these two clusters. So arbitrarily I can or randomly I can choose, say I can choose M1 as 4 and M2 as 12. You are free to choose anything. So this becomes 4 and this becomes 12. Okay, fine. Now, what you do is that you calculate the distance from this mean to all the points and this mean to all the points. So this is nothing but what you can do is that you have to have this say x1 minus m1 and x1 minus m2. This. So the minimum will be whatever minimum among these two will mean. So if suppose this is minimum, then x1 will be kept in the first cluster. If this wins, then x1 will be kept in the second cluster. So similarly, all the points will be reclustered. So what will happen? What will happen is that these 5 points will be distributed across these two clusters. Fine. So say suppose if I say that okay fine, then for say 9 and 12 is coming in first cluster, 26 and 36 coming in second clusters. But remember that already you have chosen this 12 as mean in this cluster, so certainly this 12 always be in this cluster. So this cluster, these 4 and 9 will be in this cluster and this. Now what you have is that you go for M1 dash and M2 dash. M1 dash and M2 dash is nothing but average of the points within this cluster, and then this is average of mean of points in this cluster. So take the mean of this two and take the mean of this two, that becomes your mean 1 dash, mean 2 dash. When you get this mean 2 dash and mean 1 dash, now again the same, that find out the minimum of this x1 minus m1 and x1 minus mu. This becomes now is m1 dash and m2 dash, and minimum will win. So accordingly you will find that okay, there will be readjustment, like it may be the case that 4, 9, 12 may come here, or 25, 36 may come here. and again you'll be going for M1 double dash, M2 double dash. So what will happen is that in this case, uh, this iteration will go on till you get the same set of clusters in two successive iterations. Then you stop. That means there is no changes occur in the clusters or cluster points. Then you can stop the iterations, and whatever clusters you get out of it is actually your final clusters with this k-means methods. So it is very easy to implement. Simply what you can do is that fix k first. So number of clusters is very much user defined. Then randomly choose the mean based on how many clusters you have considered. So if it is 2, then 2 means. If it is 3, then 3 means. If it is 4, then 4 means. Randomly you can choose any of these and all. And then you calculate the distance with the mean to all the points, and minimum will win, and the points will lie in that cluster. So whatever clusters you got, again go for a improved mean, and the same distance calculations, minimum will win, will go on till you get the two successive clusters are not having any changes. Then you stop it and you get the final clusters out of this method. So this is what k-means does. Okay, so I'm just leaving today with this, that how this cluster is important, what are the data types, what are the mathematical foundation you require for clustering, and then what are the categories of clustering, and then just introducing this k-means part just to have, so that you can have this assignment also. Next class I'll be coming with some another example of k-means also, and some other partition based algorithm, then hierarchical, and then we'll go on. Okay, fine.